So last time we started this section, 8.2, over integration by parts. And the motivation for this section, which we've talked about a little bit, is that we looked for a way to reverse the product rule because we need some way to do integrals of functions that are being multiplied together. And we didn't really have a method before now to do that. And so we took the basic product rule and we did a little bit of rearranging. We integrated both sides of the equation to come up with this new rule for integration by parts. So this rule is a little tricky to get a hold of it first. Part of the difficulty is that here on the left side of the integral, we're looking at a function and then a derivative v prime. And on the right side, we need this function u times the antiderivative of v. And then over here in this extra integral that gets tagged on, we need a derivative of u and the antiderivative of v prime. So I gave you some hints on how to choose u and v, or really choosing v prime in your original integral. And the guidelines were these. U should have an easy derivative. So we're going to eventually take a derivative of u. That means it should have an easy derivative that's simpler than what you started with, or at least that's the hope. And then v prime should have an easy antiderivative that's hopefully not any more complicated than what we started with, or at least not very much. And if you make smart choices for u and v prime, this integral over here should be easier than the integral that you started with. And we saw that in a couple examples last time, and then we're going to work through a few more this morning. So in this first example that we did, we were looking at the integral of x times sine x. And we know that x has a really easy derivative. It's just the number 1. And sine x has a fairly simple antiderivative, minus cosine. So when we made this choice of u and v prime, we were able to simplify our integral to get to an answer. And number 2, we learned a little bit of a trick. Sometimes if you're stuck, if you don't have a rule to go forward, you can create an extra function by multiplying by 1, and then using this 1 as your v prime, and then whatever was there originally as your u. So using this trick, we were able to find an antiderivative for log x. It's this rule here. And I mentioned that you should probably have this one in your memory bank, or at least remember that you can do this to get this rule for log, the natural log. Before we do a new example, does anyone have any questions that you've thought of? Okay, so since there don't seem to be any questions, let's go on to number 3. So in number 3, we're looking at the integral of x squared times e to the x. And we don't have a rule for this kind of integral where you're multiplying a power of x and an exponential function. So we're going to need to use our new rule, integration by parts, in order to complete this one. Let's just adjust this so that we have plenty of space to work. So we have to choose u and v prime if we're going to use integration by parts. And keeping in mind my hint that u should have an easy derivative and v prime should have an easy antiderivative, does anyone have any thoughts, any ideas on what we might pick for u and v prime?
I put x squared as u and e to the x as v
Okay,
prime.
good. Yeah, those are good choices. Because when you take the derivative of x squared, you get a smaller power of x. And when you find an antiderivative for v prime, e to the x, nothing happens. We know the antiderivative of e to the x is just e to the x, or e to the x plus a constant. So u prime is 2x, and v, finding an antiderivative for e to the x, is e to the x, like I just said. And we don't have to worry about adding a constant at this point, because we're going to add it on the very end of our integral when we're finished. Just as long as you pick a good antiderivative, we don't have to worry about adding an extra constant. Okay, so let's think through integration by parts. Maybe I should write the formula down here. For reference. And I don't think I've said this really explicitly, but of course, integration by parts is something that you need to have memorized. You don't want to have to look this up every time you do it on your homework or your exam, so definitely try to memorize this rule. Hopefully by the time you're finished with your homework, you'll have it memorized just because you've used it enough, but if not, you might need to review. So we need, in our rule, u times v, that'll be x squared times e to the x. And you'll notice this is what we started with in our integral, the original integral. And then we have a second integral that we'll have to do. We need u prime times v, so that'll be 2x times e to the x. Or if we wanted to simplify a little bit, we could pull that constant to the front. So pull the 2 to the outside, and then inside your integral, you have x e to the x. So the question is at this point, can we do this integral here? Can we find an antiderivative for x times e to the x? What do you think? Do we know one? Well, we don't, right? We still have a power of x, x to the first power in this case, times an exponential function, and we don't have a rule for this. So we'll actually have to do integration by parts a second time. So let's come over here to the right and work through the details. Maybe scoot my camera over slightly. So we need to again pick u and v prime. What do you think? What should our choice of u be? What should our choice of v prime be?
U be x and v prime be e to the x.
Good. So if you have to do integration by parts a second time, it's good to be consistent. Since we picked u to be our power of x function before, we should stick with that choice. And this idea is reinforced because when you take the derivative of x, you get 1, which is much simpler than what we started with. And then v itself is the same as before. Since v prime is e to the x, v is e to the x. Okay, so copy down what we had. And then at this point, we have to be really careful with our minus sign and, well, the constant 2 as well. So what you'll want to do is write -2 and then some big parentheses or some big brackets or something. And then we're going to do our integration by parts inside of the brackets. So be careful here. And make sure you keep the minus sign. And inside the parentheses, we need this again. We need uv prime. That's x. Excuse me, we need a uv. That's x e to the x. And then we need a minus. The integral of u prime, that's 1, times v e to the x. Before we do this last integral, let's go ahead and distribute this -2 into the parentheses or the brackets here, as I've written. So copy down x squared e to the x, then we'll get a -2 x e to the x. And then here's where we have to be careful again. We have a -2 and an extra minus sign here. So that becomes a +2. And then we can drop the 1 here in the integral to make it a little simpler looking. What's the integral of e to the x? What's the final integral here?
E to the x plus c.
Good. Yeah. So this last part of the problem is where we have to worry about having our plus c adding an extra constant on the end. So this is our antiderivative here. You might notice a little interesting pattern in our answer. You can see that we took derivatives of x squared. So we have x squared, 2x, and then 2. And then there's this alternating pattern in the sign. We have a positive, negative, and then another positive here. Are there any questions over this third example?
On the test, will it be like, will it say that it wants us to do integration by parts, or is it like, oh, we don't know, we don't have a rule, so we'll do this?
I would say be prepared for both kinds of questions. There will be problems on the test where you're just given an integral and you have to pick which method is going to work. So figuring out which method works on which kind of problem is part of what you learn as you practice on the homework and pay attention to the examples in class. Are there any other questions? That was a good one. Okay, so up next is this problem number 4. We're going to look at an exponential function, e to the x times sine x. So once again, we have two functions being multiplied together, and we don't have a rule to deal with the situation. So our instinct, since we have two things multiplied together, should be to use integration by parts. So by now we have a little bit of practice we know we have to pick u and v prime. And this one, it's a little bit tricky to pick u and v prime because my hints don't really help. The derivative of e to the x is e to the x. Its antiderivative is the same. And then the derivative of sine is cosine, and its antiderivative is minus cosine. So there's not really a great deal of difference between these two as far as their derivatives and antiderivatives go. So we just have to make a choice. I'm just going to go left to right in my choice. I'll say e to the x is u, and v prime is sine x. And then u prime, the derivative of e to the x is e to the x, and the antiderivative we're going to have for v prime is minus cosine of x. So let's box this in. Try not to smear it too bad. So we need u times v. Remember, integration by parts. We have u times v. That's e to the x times minus cosine x. And we have minus the integral of u prime times v. So that'll be e to the x times minus cosine x. And let's just make this look a little nicer by putting the minus signs where they would normally go. So we'll pull that one to the front. Minus e to the x cosine x. And then over here we have two minus signs. So we'll have a plus sign in front of our new integral. So what we've ended up with this second integral is actually very similar to what we started with. We have the exponential e to the x times a trig function. So what I would do is just make the same choice, because we're definitely going to need to do integration by parts again. So let's stick with u equals e to the x, and then our trig function will be v prime. Make sure that fits here in the picture. So the derivative of e to the x is e to the x, of course. What is my antiderivative for cosine? Someone remind me? Anyone?
It's sine x.
Sine x. Thanks. Good. So we'll do this for our integration by parts on the next step. Copy down this first bit that we don't have to worry about anymore, since it's outside of our integral. And now we have a plus sign, so we don't have to worry about it quite as much as we did last time when we had the minus 2. We don't have to worry about distributing a minus. So we need, for our integration by parts, u times v. So that's e to the x sine x minus the integral of u prime times v. So that's e to the x sine x. Okay, so what do we have at this point? We have some stuff. We don't have to worry about this because it doesn't have any integrals on it anymore. This is where we're paying attention here. So compare this to what we started with. What do you think? What do you notice?
It's the same.
It's the same. So if we tried to continue doing integration by parts, we would see that this pattern would repeat because we would pick again, e to the x for u, v prime would be sine x, and then we'd get this stuff, and then we'd have this integral again. We'd do this, this integration by parts, and then we'd be back again where we started. So we don't want to do that, of course. We don't want to get stuck in an endless loop. So what we're going to do instead is a little bit of algebra. There's a little trick here that you might not notice until you've seen it. So let's write down the equation that we have here. So the integral that we started with is equal to our last step. Let's just write that. And then see if we notice anything. So think about this integral as an unknown that we're trying to solve for. If we think about it that way, we know that in algebra, using algebra techniques, we can move something from this side of our equation to the left-hand side by simply adding it to both sides of the equation. So I can get rid of this over here by adding it to both sides, and I'd end up with 2 copies of it on the left. But there is a little bit of subtlety here since we're doing calculus and not algebra. Since I have an integral on the left and there aren't any integrals on the right, I now need to add a plus c over here. Because we know when we take the derivative of this, the constant will go away. So I can add any constant and get a different antiderivative, as we know from calculus 1. So I now have the integral just on the left side. There aren't any integrals left on the right. The only thing left to do is to divide through by 2. So the final answer when we divide through is this. We just have this whole expression over 2. And you might notice that we could factor out an e to the x if we wanted to simplify even further. But I'm just going to write it like this. So if we wanted to simplify this, we could factor out the e to the x and the 2. But not necessary, because this is the answer, no matter how we write it. Okay, are there any questions?
Was there anything that's for us to see this sooner, or we're just going to, is the only way to know to do this is when you actually discover a loop?
So this is actually the soonest that we could have done this little trick. But yeah, if you notice that you're stuck in a loop, then probably there is something that you can do like this to figure out the problem. On your homework, I can just tell you, I can give you a hint. You're going to have to find an integral for e to the x times cosine of x. And for that problem, you'll want to keep this trick in mind. It'll look a little bit different since you have a cosine, but it'll work very, very similarly.
Okay, yeah, I just didn't know if it was possible to, if you could look at a problem like and know that that's the way this one's going to go or not. So just kind of, okay.
So if you have experience with these kinds of things, you'll know that the derivative of e to the x is always e to the x. And when you take derivatives of sine, you're going to be alternating between cosine and sine. So if you keep those two things in mind, you might anticipate at the beginning that you might have this repeating pattern. And that's why it works for cosine as well, because when you take derivatives of cosine, you get, sines and cosines repeating.
Okay, thank you. That makes sense.
Mm-hmm. Any other questions before we move on? Okay, so if there aren't any other questions, let's try this next one. So we're looking at the integral of sine to the n of x dx. And I should put in a note here that n can be any positive integer. So it's something like a variable. But it's a positive whole number. And we're trying to come up with a rule that will work no matter what positive real number is here. So it could be a 1 or a 2 or a 3 or a 55 or a 5003. We're just looking for some kind of rule that could help with this integral. So you'll notice on the table of integral formulas that we know, we do have a rule for sine x by itself, but not when we have powers of sine. So we will have to do something different now, and we will be using integration by parts, as I'm sure you can anticipate. But in this case, it's not obvious what functions, what functions are being multiplied together. But we have to remember what powers really mean. So if we have a power of n, that means we're multiplying sine of x by itself n times. So I'm going to use that to help me in my u substitution by breaking off one of the powers. Let's see if I can silence that. There we go. Okay, so I'm breaking off one of the signs, and I'm going to leave the rest of them in a group together. So when I do that, it'll look like this. We have sine to the n minus 1 of x, and I've broken off the 1 over here. And these are going to be my two functions. Sine of n to the x, sorry, sine to the n minus 1 power of x times sine x. And I'm going to pick this one, sine to the n minus 1, to be my u, because I can actually find a derivative of this. It would be hard to find an antiderivative, but we can find a derivative. And then sine x is going to be my v prime. because we know how to find an antiderivative for a single sine function. So u prime will have to use the power rule and the chain rule. So we need to bring the power to the front and decrease it by 1. We get an n minus 1, and then sine to the n minus 2 of x, and then the inner derivative is cosine. And I'm running out of room here at the edge of my paper, so let's just write v below it. If v prime is sine, then v should be negative cosine. Okay, so now that we have u, v prime, u prime, and v, we can do our integration by parts. We need u times v. That'll be a sine to the n minus 1 of x, and then v is minus cosine. Okay. And then we need to subtract the integral of u prime times v. So that'll be n minus 1 sine to the n minus 2 of x times cosine of x, and then times v, which is minus cosine of x dx. And let's put a box around this. Make things a little neater, since things get a little messy when we're using variables in our integrals. This extra variable n from the exponent. There's a little bit more writing to do. Okay, so let's clean things up, make things a little bit neater in this expression. This minus sign, we will want to move that to the front where we normally put constants. So we have minus sine to the n minus 1 power of x times cosine of x. And then we have this constant here that we'll want to pull out. And we also have a minus sign, so these two minus signs will cancel. So we'll end up with a plus n minus 1. And then we have what's left in the integral, which is sine to the n minus 2 x, and then 2 cosines, so that's a cosine squared. Okay, so here was the trade-off that we managed. We started with sine to the n power, and what we did with integration by parts was we transferred 2 of those powers into a cosine. So what can we do next? What do you think?
Would you have to integrate by parts again?
If we integrated by parts, we would get stuck in a loop. Because when you take integrals of sines, you get cosines, and you take derivatives of, you get cosines as well. So we'll get stuck in a loop if we try to do that. Is there anything else that we know? Maybe, so like I said, we had a trade-off between sine and cosine, and we ended up with a cosine squared. Can we use cosine squared? Is that useful? What do you think? Do we know any formulas involving cosine squared? Any famous formulas named after a Greek person, perhaps?
Pythagorean theorem.
Right. Yeah, the Pythagorean theorem. Let me write it over here in this blank space. So the Pythagorean theorem for cosine and sine says that cos squared of x plus sine squared of x is equal to 1. So if I move the sine squared to the right side, we see that cosine squared is equal to 1 minus sine squared. Okay, so I'm going to use this over here in my integral, and we might have to flip over to the back of the page to finish here. So copy down the first part, the minus sine to the n minus 1 of x cosine x, and then replace inside the integral cosine squared with 1 minus sine squared. Okay, so I need to stop here. We're going to run out of room and move on to the back of the page where we're going to finish this. So I'm going to go ahead and write that last line down again. Okay, so here's where we finished on the other side of the page. What we're going to do now is distribute our sine function into the parentheses and then break this into two separate integrals. So we have minus sine n minus 1 of x times cosine x. And then we have two integrals, like I said, n minus 1, and then the integral of sine to the n minus 1 of x times 1. So that's just the sine n minus 2 of x dx. And then we'll distribute across the minus sign. So we pick up a minus n minus 1. And then we'll add these powers of sine to those to get sine to the n of x dx. So that seems familiar, right? Sine to the n of x dx. That's where we started. So over on the left side of this equal sign, I'm going to write where we started, sine to the n of x dx. So this problem is very similar to the last one, where we looked like we were going to get stuck in a loop, but we can actually do an algebra trick to finish it off. So both sides of the equation, we're going to add n minus 1 times the integral of sine to the n of x dx. So over on the left side, well, these are going to go away on the right. On the left side, when we add 1 plus n minus 1, that means we get n. N times the integral of sine to the n of x dx. And remember, when we canceled this off, just like in the last problem, since we're doing calculus, we have to remember to add a constant. So let's copy all of this down. What's left over? There's still this annoying n in the front, and we can get rid of it by dividing through. So let me write the rule cleanly, because this is an important formula. And this is more like you'll see it written down. So I'm just dividing both terms by n. And actually, I said we need the c here, but we still have an integral on the right, so we don't have to worry about it. Okay. So this is the rule. This is where we're going to stop. So you can see what we've done. We started with a sine to the n of x dx, and what we ended up with is a new integral where the power is lower. And this formula that I boxed here is called a reduction formula. So it's called reduction because you've reduced the power of sine. And the idea here is that if you start with, say, sine to the fourth power or something like this, you would end up with an integral with a sine squared over here on the right. And then you could apply the rule again to reduce that power down to 0. So you can apply this formula repeatedly to integrals with powers of sine to reduce the power down to either 1 or 0, depending on if you start with an odd or an even number. Okay, are there any questions over that example?
I have one question.
Yeah, go for it.
How are you able to replace the sine squared or cosine squared with, I'm sorry, the sine squared with a sine to the n?
Are you going from here down to here?
Yeah.
So when you multiply sine to the n minus 2 times sine squared, you add the exponents. So n minus 2 plus 2, you get rid of the minus 2.
Okay, thank you.
You're welcome. Okay, so that looks like it needs to be our stopping point for today. I did have one more example with a definite integral, which I might just do at the beginning of class next time. It's not as hard as these. It's just a problem with a definite integral instead of an indefinite integral, like the ones that we've done so far. Do you guys have any questions for me? Anything that you haven't already asked?
Not about the lecture, but I did notice the other night looking on my Blackboard grades, it shows the pre-course assessment as a 4 out of 10.
Okay. So the reason why it shows up like that is because the grades are imported automatically from MyLab Math as your actual score. So what I'm going to do is go in manually at the end of the semester and change that to just a completion. So that will be counted as full credit at the end of the semester when I calculate your grades.
Okay, that's what I figured. Just checking.
Yeah.